as of today, the aim is we are going to recall in terms of more variables functions, and then we are going to learn on how to normalize your radial part respect to the complete solutions to hydrogen atom. Okay. So in class we see that if you are given a 3 variable functions f, x, y, z, you can always map these to another coordinate system. So we are doing spherical. Why? Because the motions that involve two body system, which is electron, neutron, or proton, is circular motion or ellipse. Okay, so that's why we use spherical coordinates. So spherical coordinates, we have r, theta, and phi. So r is your radius, and the other two are the angles. We can always map these to another multiplications of, look at here, one variable function, and then you have multiplications of two variable function. So this is just a functions respect to r, okay, it's partial or on the radius part. And the other one is the angle, so this u means the spherical harmonic. Spherical harmonics, or you can see that this is the angular part. Angular part or equations. Alright, so your r here is the radial. This one is the radial part, this part. Alright, but you can map this further. Look at this part. So this is a product of 3 one variable functions, respect to r, respect to theta, and respect to phi. So in class you have know that you can have the complete solutions as exponential Im phi. Okay, we are going to look at this later on. So in 3 dimensions, I would want to highlight that you need to identify the quantum number. So you have 3 important quantum number. So in this case, you have n, l, and m. So you have the principal quantum number, and then you have the angular, and then you have the azimuthal. Okay, and this takes some value, so your m will take from 0 to n minus 1, and then your m is plus minus l with, okay, from 0 to plus minus l. And then your n for hydrogen atoms start with from 1 to blah blah blah. Okay, so you cannot have your n start with 0. If we do this in terms of the CAD notation, so you will write it like that. So if your n is 1, then the only variable L is 0, so you can have 1, 0, 0. So that will be your ground state. So in this case, the ground state of the electron in the hydrogen atom is psi 1, 0, 0, and then so 1, 0, and then 0, 0, and then also equivalent to the CAD 1, 0, 0. Okay, so I put here some list of the solutions to the Schrodinger equations involving hydrogen atom. So here, respect to the Laguerre polynomials, this will appear for the radial part. For the spherical harmonic, you see for 1, 0, 0, or you can write it 1, 0, psi 0, 0, theta phi. So this is 1 over pi square root 4 pi, and so on. Okay, you can always get it in terms of the invertible coordinate. For a several case of your radial part, see this one. Okay, several on the radial. So this is start with R naught. So we are going to show that this part is the normalization constant. Okay. A bit on your energy. So the energy, the lowest energy n here, if your n is 1, is given by negative 13.6 electrovolt. So if you want to build up more n, okay, so you can have n 1, 2, 3. So you can build up your n. The second, the up to n is from here. Okay, So if your n is 1, you get back your lowest energy. So your n is 2, so you just substitute n over there. For this part is how you look at the complete right up respect to the radial part. This one is for the radial. And this one is the orthogonality of your Laguerre functions, okay, associated Laguerre functions respect to R. So you see here. So these functions, it is have an orthogonality but not normalized. So once you find the normalization constant, compute it like that. So you can just compute. So next is we want to find the normalizations of the lowest ground state. So sometimes in my notes I have A or A naught, but let's say just put A naught here. That will be a bore radius. So we want to compute C naught to obtain or verify C naught. So this is the constant, okay? It's always in terms of the bore radius. So let's move on. So how to compute this, how to normalize R1 naught. So remember, this is the ground state, which is compute C naught. So we use the integral from 0 to phi. So R square multiplied with the absolute square of your R and L dr, make it equals to 1, because we want to compute C naught, okay? So what we do, you just substitute. So from here to here, you find square. So remember, you have C naught over A. So if you want to put it square, you also C naught star over A. So this implies C naught square over A square. You get this one. And then you have exponential R over A multiply exponential R over A, because you square them. So you add this together, exponential minus 2R over A. So that's why you get this one, okay? And then you have R square. This is already in the integral because we change our variable. So you end up with equation 2. So usually there are two options. One, integration by parts. Everyone know how to do this. How to, okay? But today I'm going to teach you to use special functions or gamma functions, which is more, I think, easy for you to handle, okay? So this gamma functions is denoted by this. So this is uppercase gamma function Z. So what is this gamma function? So see, look here. So look at this definition. So gamma functions is gamma n. So whenever you see this, the computations on the right hand side is n minus 1. Or in terms of the integral, if you have a gamma functions respect to variable z, this means that you integrate from 0 to infinity a z power of n minus 1 and an exponential minus ez, dz. So you look closely here, you have some r, and then you have respect to r. Your r here, power of 1. So your z here, power of 1. So you can use gamma functions. If it's a power of 2, you need to use the Gaussian identity, okay? So how we handle this gamma function? So if you have gamma n equals to 2, then the solution is 1 factorial. So this is factorial. If you have gamma 1, so you have 0 factorial, which is just 1. So if you have gamma 3, you have 2 factorial, which is just 2, and so on. You can continue. So next, let's try to do this. From equation 2, okay, so from equation 2 you have that. So you have C naught. I teach you how to do change of variable, okay? So let's try to look it here. Let's do change of variable. Let's put U equals to 2R over A. So this means that your R is UA over 2, okay? So your du over dr is 2 over A. And then you can find dr is A over 2 du, okay? You just manipulate the algebra. So now we do change of variable, but I need r square. See, r square there, this one. So r square is u square A square over 4. Okay? All right. Now we substitute. So for r squared, you have u squared a squared over 4. And then exponential just minus u, because this one, 2r over a is u. And then it's become du, but your dr is this. So you substitute a over 2 du. So now everything here is in terms of u. We rearrange, so all the constant we can put it outside. So you have a squared, and then you took out a cubed because of that, and then you 8. So you end up with, oh sorry, this is infinity. So you have u squared e minus u du. Now this is very lovely. You can, so you have 2a to the power of 1, and then you have c naught squared over 8. Okay. Now look at this part. So you want to compare this with this one, equation 3. So your u is 2, so compare with z to the power of n minus 1. So the order must be the same. So n minus 1 must be 2, so your n is 3. Then you can compute n is equal to 3. So therefore your gamma is 3 is equals to 3 minus 1 factorial equals to 2 factorial. So to solve the integral, so this is actually 2 factorial. Let's go back to black. Okay. So you can simplify. So you have a c naught square over 8. Maybe we just simplify accordingly. So 4. Okay. Make it equals to 1. Rearrange. Don't mess up in this case. So a. So your c naught is square root 4 over a is become 2 over square root a. So what will be given? So you have r naught is c naught over, let's go back here, c naught over a naught, c naught over a naught, a or a naught, okay, the same thing, a naught, okay, a naught, and then you have e exponential, okay, you have r over a, so you just substitute 4 over a naught. So 1 over a naught, 4 over a naught, exponential minus r over a, simplify, you have 2 times a to the naught to the power of negative half e minus r naught. So you should check that this is the normalized radial part, okay? So that's it. Please do you try it in BLAS. You try it, where you will compute or verify R20. Thank you.